Okay, so today we're going to talk about our first more advanced data structure, which are basically linked lists, and we'll get into it with a little bit of motivation as to why we want to do this. So far, we've seen ways of organizing data such as arrays and dynamic arrays, but why would we want to organize it differently? And one of the reasons that we want to organize it differently is arrays are pretty easy to use, but they have some problems. One, the array size is fixed. Two, searching for items in an unsorted array is slow. Basically, we have to do sequential search in that case, and inserting items into a sorted array can be pretty slow since it requires a lot of data movement. We solved this first problem, arrays being fixed in size, by using dynamic arrays, which we could grow and shrink in size, and certainly vectors solve a lot of problems as well. So also, dynamic variables are seldom just int, double, and char, and we'd like to give more information. In particular, we can use something called a node. And nodes are implemented as structs or classes, and basically they include a pointer to the next node so that we have a way of relating one object to another. And that's the definition of a linked list. We'll get a more formal one a little bit later on in the presentation. So here's an example from the Malik textbook. Here, head is a pointer variable that points to the first item in the list. Each node contains data and a pointer to the next item. So we start at head, it points to the first node points to the second node. So there's a way of relating each node in the list to another node. The last one will point at null, which terminates the linked list. So how do you make such a structure? Well, basically, a lot of times you can have them implemented as structs or classes. In fact, you always have them implemented as structs or classes. So basically, we have struct list node. In this case, we're making a grocery list. There's string, which is the item name, a count, and a link to the next item in the list. After that, to make things easier, we type def pointer to list node and call list node pointer. This does seem somewhat circuitous, but we need to define the list node itself before we can make a pointer to it. So some notes on this definition. We need to make a pointer variable to the head of the linked list. So we basically do list node pointer head, and then list node must come before the list node pointer. Again, like I said on the last slide, that's because we need to define list node before we can define a pointer to it. So, there looks like there's a bit of circularity in the definition, but there's no circularity there. It appears to be on the surface, but it's actually not. So we can change items in the head, and remember that the dot operator has a higher precedence than the dereferencing operator. So we have to dereference the pointer to head inside of parents to give it higher priority, and then get the count. And that would change the count to the command in the first bullet point would change the count to 12. Head is a pointer variable, so again, star head is the node that head points to, and we need those parentheses because the dot operator has higher preference than the dereferencing operator. And that seems pretty hard, but as we discussed earlier in the class, there is an easier way. And the easier way is to use the arrow operator, which combines star and the member access operator. So if we're using dynamic memory, we can do head arrow count and then set that equal to 12, or change the item head arrow item is equal to bagels. So we wanted to get bagels instead of donuts. So again, you can access the individual item at the head of the list by doing head count and head item. And those will get the member variables of that struct. If a node doesn't have a following node, we use null as the end marker. And null has two purposes. One, it gives a value to a pointer that ordinarily wouldn't have one. So it technically does have a value, and we use it as an end marker for the linked list. The value of null is technically 0, but think of it as null and try not to conflate the two in your programs unless you want to enter the International Obfuscated C Programming Contest. Any pointer can be assigned the value of null, so I can declare a pointer called there that's of type double and set it equal to null. And you can find null in several libraries, including IOStream and C standard def, and C++ 11 and onward has null PTR as a definition, so you can use either one. So a linked list formally is a list of nodes in which each node has data and a member variable that is a pointer that points to the next item in the list. The first node is called the head. The pointer variable head points to the first item in the list. And the last node contains a pointer that is set to null. And that gives you a formal definition of a linked list. So let's simplify our previous definition to cut down on the amount of code we have to write. So here we're just going to need a value rather than a string and a value. So we do struct node, and we have data that's in that node and a pointer to the next item in the list. Again, I use type def node star to be node pointer. You could declare node star at every step of the way, and that would be perfectly fine. There's more than one way to program in C++. So let's get to constructing a list. We start with the head. So we make a node pointer to head, allocate new memory for the head. Again, these are dynamic data structures. They're not static or automatic. We give values to the new node. Head data is 3 and head link is equal to null. So it's just a node all by itself. The head is also the tail or the end of the linked list. So it's kind of lonely all by itself. So we'd like to add something to it. And in fact, we can add nodes to the head of the list. So we can put one before it. So what do we need? A call by reference pointer to the head node and a new node value. And it is a call by reference rather than call by value, because you'll remember previously how tricky it was to actually have call by value pointers, if you could have them at all. So what we do is we create a new dynamic variable pointed to by temp pointer, which is a local variable, place data in the new node, and then make the link member of this new node point to the head node. So it points to where the head is at. And then move head to point to the new node that we just created. And this is easier to illustrate on a whiteboard, and we'll actually draw this out when we have our synchronous session. So the idea is we set up our temp pointer, have temp pointer point to the head of the list, and then change head to point to the temp pointer. And so that adds the new item to the head of the list. So it pushes it on to the top. In code, we basically do our list node pointer, temp pointer, allocate new memory for it, set its count and its item, and then have its link point to head, and then say head is equal to temp pointer. And you don't want to get the last two of commands out of order there. You can also specify an empty linked list just by saying head is equal to null. And always make sure that your program and its functions can deal with an empty list. Because you could have them, and that's one of the common pitfalls, is that people don't have the code to deal with an empty linked list, and the program will crash. So make sure you have something in there that can deal with the empty linked list. The other one is, as I mentioned, getting those things in the right order. So if you write a routine for inserting an item to the head of the list so that pointer variable head constructs a new node, then that's not going to work real well because you lost the original linked location. And also putting things out of order can also lose nodes, and that's called a memory leak, and can do some pretty, I would say, nasty stuff rather than sweet stuff to your program. So, if we just say head is equal to our new node without having our new node point to the current head, then we've lost all the previous information from the list, and that memory is still allocated from the free store, and that's going to create a major problem for us eventually. It may not if we only have one linked list and just a few items in it. But, if we had a program that was running, constantly and doing that and adding things, we would eventually lose enough information that we ran out of memory in the free store. Okay, so that's how we add to the front of the linked list. How about inserting and removing nodes from the middle of the list? Well, this is a little bit trickier because we need a couple different pointers. And basically, we assume that we know the node before the one we want to insert. So we know the one that's after me. We also assume that we know the value of the new node. Otherwise, why would we be inserting it? So to insert a node after a specified node, we use a function to obtain a pointer to the node that we want to insert after, and we call the new node that will be inserted, and we call the pointer after me. Use the function insert to insert the node, so it needs the one that's inserting after and what it's going to insert. We'll add a link to the new node to the list, and then add a link from the list to the new node. So we're going to update a couple of links in this one. So we declare our new list node pointer and allocate memory for it, set its count and the name of the item, and then have a link for that goes to after me's link, and then after me's link goes to the temp pointer. So basically it puts itself right in the middle there. So after me points to the new one, and the new one points to where after me used to point to. And, again, I always finish these off, even though they're void functions, with a return, just to be explicit that that's what I'm doing. So here we have our head. We have a node after me. That's the second one in the list. We make our new temp pointer, and that's our new node. We allocate the memory, and we set it equal to 5. We have it point at after me's link, so it points to the 9, and then after me points to temp pointer, and voila, it's inserted right in the middle of that list. So we'll read 2, 3, 5, 9, 18. Removing a node is similar to insertion. We need to know the node before the one we want to delete, and point to the node that's to be deleted and update the link of the item before. So before this link is equal to discards link, and we don't forget to free up the memory because this is dynamic memory. We need that delete command. So let's take a look at how this works in code. And it's probably not the best use of terminology, but the name of the function is kill node, and we basically pass it a pointer after me. So which one are we going to kill? Well, it's going to be the one after me. And so we have before and discard. So we set before is equal to after me, and discards is equal to before followed the link. So it's the one that's after me. And then before's link is equal to discards link. And so basically we skip over it and then we delete discard. So we don't have to actually do anything with the node itself. We just find the one that's before and set it equal to the link of the one that we're going to get rid of, and then we delete the one that we're going to get rid of. So functions in linked lists, for example, searching a linked list, that's something we often have to do to find something. We need to insert an item into the list, which we've covered, and delete an item from the list. So those are basic operations we want to perform. And one of the another type of operation is a traversal. So basically we want to give it, start at the first node in the list, step through the nodes in the list, and do something to every item in the list. This could be printing them out, could be adding them, could be searching for an item. And this is sometimes known as iterating through a data structure. So to search through a linked list, you still need your node structure. And the function should have two arguments. One, a linked list. That's basically where you're searching. And two, the value that you're searching for. The function should return a pointer to the first node that contains the value that you're looking for. We'll use a local pointer to move through the list and follow the pointers from node to node. So, how do we do that? We haven't talked about moving pointers, so how do we get through the linked list? The pointer member of the node currently pointed to by here, which is our local pointer, is given by here link. So what we do is we just basically say here is equal to here, follow the link. So here's a preliminary cut at the algorithm. So we have here is equal to head, while here's data is not equal to what we're looking for, and here's link is not equal to null. We do here is equal to here, follow the link. If here's data is equal to the target, we return here. Otherwise, we return null. So, how did we get out of that loop? We either got to the end of the linked list and didn't find it, in which case we return null, or we found it. And if we found it, we return the pointer to where we found it. So any problems with that? I can think of one, and the problem that I can think of with it is that it doesn't deal with the empty linked list, and that's one that I said to be careful of. So we need to add in some code that, will deal with an empty linked list. So if here is equal to null, return null. Otherwise, do our previous routine, and that will complete the sequential search. So I introduced the term iterator. It's a construct that allows you to cycle through data, items stored in a data structure. And that's going to be pretty important in CS321, as will a lot of other things mentioned in this chapter and the coming chapters. So we're starting to move into the preliminary material for CS321. Using pointers to move through a linked list is an example of the construct of an iterator. And there are some variations on the linked list. So one of them is ordered linked list, and this one is covered in Malik. And basically, it's usually a subclass of a linked list. The elements are assumed to be arranged in some sort of order, usually ascending order, basically going from the smallest to the largest, although you could go from the largest to the smallest if you wanted to, descending order. And you need to redefine or provide definitions for the following functions: one to insert first, one to insert last, one to search, and one to delete node. Include the function insert to insert an element in the ordered list at its proper place. So you need to redefine that one. Doubly linked list is a linked list that has a forward pointer to the next item in the list and a list to the previous. So head would have a previous pointer equal to null, and the tail, the end of it, would have a previous pointer to the one just before it, but its next pointer would be equal to null. So you can go forward and backward through this list. Stacks, basically it's a linked list where you add or remove only from the head of the list. And we're going to see stacks in one of the coming lectures, along with its buddy queue. And a queue is a linked list where you can add items to the back of the list and remove the items from the front of the list, kind of like the line at a grocery store. And finally, binary trees. A tree is a data structure that has a root at the top. You've probably seen these in 241 or somewhere along the way in your studies of computer science. Each node except the root has a predecessor, and each node except the leaves have one or more descendants. With exactly 2 descendants, you have what's known as a binary tree. So that kind of wraps it up. There are some even more variations on these dynamic data structures, and we're going to get into those. Thanks so much for listening.